Hey there, Year 9, it's Mr. Herman here, and this is lesson 5b, Factorizing Expressions. Learning goals for this lesson is to understand what it means to write an expression in factorized form, and to know to always look for a common factor before trying other factorizing techniques. The success criteria for this lesson is to be able to recognize the difference of perfect squares, including ones involving surds, to be able to factorize using a common factor or a difference of perfect squares, to also be able to use the grouping technique to factorize. There's a lot of words and a lot of terms and a lot of expressions that you've just heard from that learning goals and success criteria, which probably make no sense to you right now. When we delve into the key ideas and the different examples, they will make sense. And before we do continue with the key ideas and the different examples, if you are going to take the specialist maths and mathematics trajectory when it comes to maths for next year and VCE, all of this will tie into those type of lessons. So right now, a lot of these type of questions are skill and technique based, which at times can seem a bit monotonous and a bit dare I say pointless, but it will tie in further down the track when you look into sketching quadratics, which have a lot of real life applications. Okay, so right now this is very skill based, just like when you add or subtract and you learn those skills in primary school. Obviously they're technique based, but then you can apply it to real life application type things later down the track. So this is one of those foundation topics before you tackle some pretty intense maths with specialist maths and math methods. Okay, for now, let's look at the key ideas right here. We've got factorizing expressions. So to factorize expressions with common factors, you're taking out what's called the common factor. You're just going to take it out. So it's kind of the reverse of expanding. You're looking for something in common between the terms, take that out as what's called a common factor. So in this example here, we have minus 5x minus 20 is equal to minus 5 bracket rather x plus 4 close bracket. This negative 5 is considered a common factor, and what we're left with is the x plus 4 that's within the bracket. So when you expand this out again, this becomes minus 5 times x, which is minus 5x, and minus 5 times positive 4, which is minus 20. Now, before we continue on with this, and after this little example here, I'm going to delve into 3 different scenarios that you will face, because there's quite a bit of confusion about how to tackle common factors when it comes to negative terms. We'll get to that in a second. For now, here we have 4x squared minus 8x equals 4x bracket x minus 2. The commonality between the number parts is the number 4, because 4 is the highest common factor between 4 and 8, and the commonality between x squared and x is, well, just one of the x's. I can only take one x out. So what I'll be left with is 4x on the outside, and inside the brackets will be x minus 2. When you expand this out again, you will return back to the original expression that we started off with. Now, before I continue on, there's a bit of discrepancy behind what is considered a common factor when it comes to negative terms. So right now, I'm going to provide to you 3 different scenarios where we have to take out a common factor. And the first scenario is quite simple. Let's just change this here. We have a 5x plus 20. The second scenario is a 5x minus 20. And the third scenario is minus 5x minus 20. So these are the 3 different types of scenarios. If you just have 2 terms, one of the terms has an x involved, and there's a number involved with that x as well, so a coefficient. But these 3 different scenarios, it's a bit tricky to determine what the highest common factor is, because we're so used to looking for what's considered the highest common factor. Okay, the highest common factor. But then you kind of get confused, because when you look for a highest common factor when it comes to negative, when you saw in the previous example, we took out negative 5. Well, technically 5 is also a common factor between negative 5x minus 20, and it's considered the highest one because 5 is greater than negative 5. But then why did we take out negative 5? And it comes to this, I guess, not general rule. I had to get some clarity from both Mr. Sharper and Mr. Beard about this one, and they were still a bit confused about this. But it has to do with when you factorize, how tidy it looks. So the first example is really easy. The highest common factor, or the factor we can take out, is 5. So this right here, when we take out 5, what we'll be left with is just x. And how many 5s go into 20? 4. So this is nice and simple. Okay. This one here, in this scenario, because this is a negative, but the first term that's associated with the x is a positive, I take out the positive 5 in this scenario. So here, this will turn into x minus 4. So 5 goes into 5x once with the 5, and then the x's are remaining. So we take that 5 out, we lost forwards there. But when it comes to the negative 20, 5 times negative 4 will give us negative 20. So we have to leave a minus 4 here. Again, this is fine. Now, you'll notice that the commonality between these two, yes, there is a positive 5 at the front. The fact that this x here is positive, this is what we're trying to achieve. This is why we take out the common factors that we do, because when it comes to the last one, when it comes to this one here, I want to make sure that when I write something within the bracket, I want this x to be positive. Okay, I want this x to be like this. Okay, and the only way we can do this is if we take out a negative 5. Now there is one more scenario that I'm going to show you, but for now, this negative 5, when taken out, how many negative 5s go into negative 20? Well, a negative divided by a negative gives me a positive, so what I'll be left with is a positive 4. So negative 5 times x gives me the negative 5x, sorry, and negative 5 times positive 4 gives me the negative 20. I want this x here to be positive. Okay, that's the whole point. So this 5 that's taken out, we call this the magnitude of the number. So the magnitude between 5 and 20 is 5, and because this term here has a negative associated with it, because it's there's an x involved, we take the negative of that. So the fourth scenario that you can get is if this is negative 5x, and then we have a plus 20. So again, I want to get to a scenario where if I take a common factor out, I'm left with just this positive x within the bracket. The factor that you take out, in this case again, is negative 5. And the only thing that changes within here is changing this into a negative 4. So how many negative 5s go into positive 20? Well, positive divided by a negative gives me a negative number. Then when you expand this out, you have negative 5x plus 20, which is what we started in the first place. The alternative is if we looked at this and we just took out positive 5 as our common factor, we'll be left with this negative x minus 4. And the fact that this negative x is here, this is deemed untidy within the maths world. But in saying that, there's no fundamental ruling of this, it's just the culture that has been presented. In saying this, if you were to do this and go from here to here within a test, you won't lose marks because technically you are correct. But we wanted to have, I guess, consistency within the maths community. So we decided that if you were to take out a common factor of some sort, we want to leave that x positive. If it's at the start of it anyways. A little bit confusing, I know. Sometimes the back of the book might have some type of different solution, how they've taken out their common factor. And this is one of those things that really irks me, because there's always inconsistency between different teachers, different schools that I've taught as well. Majority of them do say that you want to leave the x as a positive when you take it a certain number out as a common factor if there are negatives involved. But hopefully I'll hunt down the final ruling or consensus, and we'll get to some, I guess, generalized form. Until then, just make sure this x is positive. Okay, all right, 10 minutes just to explain this one little thing. Okay, the second key idea is that when we factorize a difference of perfect squares, so we saw that in exercise 5a, DOPS for short. The difference of perfect squares is when two terms are squared with each other and there's a minus, hence the word difference. We can write this in the form of a plus b in brackets and a minus b in brackets, because when you expand this out again, there's a cancellation that happens and you'll be left with this. So we're doing the reverse process of what we saw in 5a. We use surds when a squared or b squared is not considered a perfect square. And a perfect square are the numbers where you have 1, which is 1 squared, 4, which is 2 squared, 3, which is 9 squared, 4 squared is 16, 5 squared 25, etc. So if you don't see these numbers within here, we use surds. So this example here, x squared minus 5 is not a perfect square. Okay, because there's no two numbers that when you multiply them together that are the same will give you 5. So when you want to write this in bracketed format, or want to factorize it, the x can be written as x because x squared, this can be factorized, so that's fine. So we have our x here and x there, but this 5 can't be, so we just put a square root around it and leave it as 5. 1 is a plus, 1 is a minus, following this format here. And we do this so when you expand this out again, you got to remember that the square root of 5 times the square root of 5, or also the square root of 5 squared, takes us back to this positive 5, which is what we have here. Okay, or just 5, not positive 5, just 5, which is what we have here. So the ruling might be confusing, but as long as you remember this rule, you'll be ace, you'll be sweet. All right, factorize 4-term expressions if possible by grouping terms and factorize each pair. So right here we've got 4 terms. We have x squared plus 5x. What we've decided to do is group this together as one part, and then the minus 2x minus 10, we group this as a separate part. I'm going to put this around here like that. What we end up having is the commonality between x squared plus 5x is the letter x. So we take that x out, and what we're left with is x plus 5 within the first part. And between negative 2x minus 10, because we want to get rid of that negative 2 out, that's why I was trying to figure out if I had to include that negative, and of course we do. The negative 2 is a common factor because we want the x to remain positive within the bracket. And so we have negative 2 comma x plus 5. The commonality between x times x plus 5 and minus 2 x plus 5 is the fact that there are 2 lots of x plus 5. This is our common factor, so we take this common factor out. How many x plus 5s are there within x times x plus 5? There's 1, so we take this one out. And how many are there in minus 2 x plus 5? There's one of them out. So what we're left with is this x and a negative 2, which remains within this bracket here. To make this make a little bit more sense, because some people, I've seen students get confused when they look at this and they're like, how do we get from this here to there? What's going on? What I'll do is I'm going to introduce what's called a dummy variable. Okay, I'm going to say that this x plus 5, let's just make this equal any letter. Okay, t. So whenever I see a t, I'm going to, or x plus 5, sorry, I'm going to replace it with a t. So here I have x times t, because this is x times x plus 5. And here I have an x plus 5 here, so I'm going to turn this into minus 2t. Now, what is the common factor between xt and negative 2t? Well, it's the letter t. So if I take out t as my common factor, what I'll be left with is x minus 2. Okay, so I've taken t out as my common factor, just like we did here. at the start we took out -5 as a common factor, and what we're left with is x plus 4. Here we're just left with x minus 2. But we've got to remember that we established the fact that t is equal to x plus 5. So let's change this to x plus 5, and what we're remaining with, which is x minus 2. Wow, that's what we had in the first place. Okay, so this dummy variable is a technique that my teacher showed me in math methods just to get a better grasp of what's going on here. But as long as you know that x plus 5 is the common factor between these two terms, you just take it out and you write down what you're left with. Okay. All right, let's put our key ideas into practice and let's tackle these set of examples. I'll see if I can try to get this under 25. Fingers crossed. Okay, factorize by taking out common factors. Common factor between -3x and -12. I want to make sure that that remains positive as an x. So my common factor is -3. So -3 gets taken out, and what we'll be left with is x plus 4. How many -3's go into -12? A negative divided by negative gives me a positive, and 3 into 12 is 4 times. So this right here is your final solution. Nice and simple. Second one, we have a 20a squared plus 30a. So there's two different components we're going to look into, the number component and the letter component. The highest common factor between 20 and 30 is 10. 10 is the highest number that can go into both 20 and 30. And the biggest component that can go into both a squared and a is just the letter a. What I'll be left with is how many 10's go into 22. And a squared divided by a is just a. So when I expand that out again, I get 20a squared, which is what we started off in the first place. And how many 10a's go into 30a? That's just 3. So 10a times 3 gives me 30a. Sweet. That works out. That's how you approach this. That second one. Third one, we can see a commonality between this term here and this term here. The commonality is this x plus 1. So I take out x plus 1 as my common factor, and what I'll be left with is the remaining from taking x plus 1. So here we have 2, and from here we have a minus a, and there is our final solution. So I know there's a big explanation behind something so simple like this. It's more to do with the next set of examples that you'll see in a second. We're going to factorize the following difference of perfect squares. You may need to look for a common factor first if that's the case. Okay. What they mean by common factor is, before we factorize, is there anything in common between x squared or 16? Is there any common number? In this case, not really. There's no commonality between the two. And 16 is considered a perfect square because this is 4 squared. So you've got to remember the format, that if it is a squared, take away b squared. This is a plus b, a minus b. Doesn't matter which order it is, as long as one is a plus and one has a minus. So what this is saying is that x squared minus 16 can also be written as x squared minus 4 squared, because 4 squared is equal to 16. And now we have this format that we can change it into, which is x plus 4, x minus 4. And that right there is our factorized version of this here, because if you expand this out again, you will return back to this original expression. For b, there's multiple perfect squares going on here. Here we have 9a squared, and we also know that 9 is considered a perfect squared number. So 9, it can be written as 3 squared, and then we have this a squared. And 2 can also be written as 2 squared. We have this b squared. Now when we go back to our indices rules, if there are two terms that are both being squared, that are being multiplied with each other, we can group them up. We can group them up like this. Because when there's a squared on the outside of the bracket, that gets applied to both the number component and the letter component within the bracket. So I can write it like this, and you'll see why. Same thing with the 2 squared b squared. This can be 2b all squared. Now we have the format of a squared minus b squared. The a is just 3a, and the b is this 2b. So what we'll be turning this into is this 3a plus 2b for the first part, and 3a minus 2b for the second part. So you can see why I've decided to group it, so I can just follow this format here. So I can recognize, hey, I can actually factorize this because this is a difference of perfect squares. This you'll see, and you don't necessarily see the format, so it's good to just group them and then realize, okay, yep, I can factorize this. Example C. Example C is this little statement here. You may need to look for a common factor first before you can do the difference of perfect squares. We do see a common factor. There's a common factor of 12. 12 goes into 12y, 12y squared, sorry. There's 12 many times, and what we'll be left with is y squared. And 12 goes into 1,200 100 times. So let's just double check. 12 times y squared is 12y squared, and 12 times negative 100 is negative 1200. Yep, that makes sense. And so now this is the thing we want to hone in on or focus on. I can see difference of perfect squares because this can be written as y squared minus 10 squared, because 100 can be written as 10 squared. This follows this format again. I'll put a thing there. There we go. So this is 12. Keep that 12, the outside. Y plus 10. Y minus 10. And that's our final solution. For the last one, we do have a difference of perfect squares. This whole term here is being squared. And so we got to write this out as one of our difference of perfect squares. Now this here is going to simplify a little bit further down. So the first step we're going to do is write this here as our squared, and notice that 4 can be written as 2 squared. Now x plus 3 squared minus 2 squared, this is our difference of perfect squares. This is our A format, so this is going to be x plus 3 plus 2 as the first term, and the second term, which I'm just going to write on the bottom, there is a times between them. This is going to be x plus 3 minus 2. So there is my A component for both of them, and here's my B component. One's being plussed and one's being minused. But then we can simplify this further down, because I know what x plus 3 plus 2 is. This is going to be x plus 5, because 3 plus 2 gives me 5. And x plus 3 minus 1, well, that's going to give me x plus 1. So this right here, even though it looks a little bit different to what we are used to within the first 3 examples, this here simplifies to x plus 3, or factorizes, simplifies it to x plus 5 in brackets and x plus 1 in brackets. Okay, so be careful of these 2 different types of examples, okay? Or this one particular example. Or maybe these 2. Yeah, you go to 12 here. I'm mumbling. Alright, next one. Factorizing difference of perfect squares using surds. Alright, let's use some surds. A. 10, not a perfect square. You can't write this as a perfect square. So you can just jump straight to writing it as x plus whatever this number is. You put a square root around it and leave it as that. So the second one will be minus. Simple. And that's all there is to it. When you expand it, it returns back to the original expression that we started off with. Second one, 24, not a perfect square. So we have x plus square root of 24, x minus square root of 24. Now many of you will probably look at this and think, yep, that seems legit, seems pretty cool. We have a little side note. So side note, this isn't the final solution. Root 24. Going back to our surd topics. Root 24, there is a perfect square that's a factor of that's within 24. So this can be written as 4 times 6, that's 24, which separates to square root of 4 times square root of 6. So this is 2 root 6, as the square root of 4 is 2. So this square root of 24 should technically be written as x plus 2 root 6, x minus 2 root 6. You need to hone in on your simplification of surd rules. Okay, I can't accept this, because this, while it is using the factorize and different perfect squares using surds, you need to simplify your surds down. That's the whole reason why we focused on simplifying surds. Okay, you need to show this working. Root 10 you can't do, because there's no perfect square number that is a common factor of 10, or that's a factor, sorry, of 10. In 24 there is, and that's 4. Okay, see, last example, and then you guys can stop hearing me talk to myself. I am teaching you guys. Okay, so we have x minus 1 squared and minus 5. So this is going to be x minus 1 plus, because 5 is not a squared number, so we put the root 5. There's the first part, and the second part I'll put at the bottom, x minus 1 minus square root of 5. So remember, this was the first component part here that's squared with your plus, and this is the first component again here, from here with the minus. Luckily for you guys, you don't have to simplify down this anymore, because it can't be simplified. So this is your final expression or final solution. Okay, that's me done. Check your log sheet, see which questions you need to do. You've got this lesson, which is Thursday's lesson, and the weekend to work on this, because we're then going to continue on with exercise 5C next week. You know where I am if you need any help, and I'll see you guys in the next video. Tell you.